Hey guys, hope everybody's doing okay. What we're going to do today is continue with our unit on kinetics, so we're going to talk about the Arrhenius equation and catalysis. Catalysis is really just focusing on catalysts and how they affect the reaction pathway. First part of the lesson is pretty short. It's on the Arrhenius equation, so you can write that down on your note sheet, and it looks like this. It's K equals A times E. All of that is raised to the negative EA over RT. Alright? You know what most of this stuff represents already, so K is your rate constant, E sub A is your activation energy, R is the gas constant, 8.314 joules per mole Kelvin, and T is the temperature in Kelvin. A is something new, we haven't really seen that before. It's called the frequency factor. And all that is a measure of the probability of a favorable collision. Okay, so probability of a favorable collision, and that's something that would usually be given to you. Now, in the current format of the AP test and the current curriculum, the Arrhenius equation is not on your note sheet, and you're not expected to do any calculations with it. The main reason I show it to you is so you can see the relationship between activation energy, temperature, and the rate constant K. Alright, so that's why I want to show this to you. So, a couple questions on your note sheet. One of them says, what happens to K as the temperature goes up? So just look at the equation and do some math here and figure out what's going to happen as the temperature increases. We know already from previous experience that as the temperature increases, the rate of your reaction should increase as well. So temperature is right here in your Arrhenius equation. And again, this is the same guy who did the work on acids and bases and obviously the work here with activation energy. As you increase that temperature, your denominator of the fraction is going to get larger. So what's going to happen to the overall fraction? Well, as the denominator gets bigger, the overall fraction here, this whole thing, in like the weird parentheses I have, that whole thing gets smaller. So you would think, well, if you're, and that's an exponent, right? Because all of, like the A times E is all raised to that. You're going to say, well, if my exponent is small, my K value, my rate constant, should go down. But it's a negative exponent. So as your negative exponent gets smaller and smaller, the actual number, K, gets larger and larger. Okay, so there's a lot of different layers here to the math, obviously. It's not anything that's overly difficult. But temperature increases gives you a smaller negative exponent for your what you're raising everything to here, which means an overall larger K value. Right? So you just plug some numbers in if you want to. Plug in a random number for E sub A, plug in your 8.314 joules per mole Kelvin for your R. Just make up some frequency factor here, and then just try some different temperatures, and you'll see that the K will increase as the temperature increases. All right? And then what happens to K as the activation energy decreases? It's really the same thing. As the activation energy decreases, you should have a faster rate of reaction, right? Because activation energy is that energy needed for effective collisions and for the reaction to proceed. So the lower that is, as the activation energy decreases, you should have a faster rate of reaction, a higher value for K. And that does happen here. Same reasoning as the previous example. So if you're E sub A, that's your activation energy. As that decreases, it makes this whole fraction smaller. But again, it's a negative number here. It's negative E sub A over RT. So you're making a smaller and smaller negative fraction, which is your negative exponent here, which is good. That's going to help you increase the value of K. So again, plug in random numbers and you can see how the math works out. Pretty straightforward stuff. So how does a catalyst speed up the rate of a reaction? Well, catalysts lower the activation energy. So they speed up the rate of reaction by doing that. And we're going to look at some different pathways involving catalysts in a couple minutes. Okay, so that's what we're going to focus on next, and that transitions us from the Arrhenius equation into catalysis. If you take your Arrhenius equation now, if we wrap this up real quick, take the natural log of both sides, you get this format of the Arrhenius equation, which is ln K equals negative E sub A over R times 1 over T plus natural log of your frequency factor A. If you take a look at it, that's actually in the y equals mx plus b format. So you could actually graph this. So if you have a lot of data available, this method could be a good way to find the activation energy. So if you have your rate constant, you're going to, you have that. You're going to have R always. If you have your temperature, your frequency factor, you could solve this for E sub A and figure out what your activation energy actually is. So if you plot this, make a plot of natural log of K versus the inverse of temperature. Okay, so that's your y-axis obviously over here, and your x-axis here. Go back to your Arrhenius equation manipulated format here. You see your y is natural log of k, and your x is the inverse of temperature. And your slope is going to be negative EA over r. And you already know the r value. All right, so you can see that here. Slope is negative EA over r. So if you could plot natural log of k versus 1 over temperature, find the slope, and then you end up with your negative EA over r. You know what r is, so you could easily solve for activation energy. It's just another graphical representation of some data which I wanted to show you and how it is involved with activation energy. Okay, so again, you're not going to memorize the Arrhenius equation. You're not going to do calculations with the Arrhenius equation. It's just 5 minutes of some background information here on it and how it applies to activation energy and some of the other data you can have in a reaction. So moving on to catalysis. Pretty easy, straightforward stuff here. You already know a catalyst changes the rate of a chemical reaction by lowering the activation energy, and we actually have two different types of catalysts. We have homogeneous and heterogeneous. So we're going to take a look at homogeneous catalyst first. And this is just a catalyst where the catalyst itself and the reaction are in the same phase. So you know what homogeneous means. This is the same thing. So you can see chemical reaction occurring. This is just the decomposition of hydrogen peroxide. So H2O2 yields 2H2O plus O2. And I did this demo for you guys in class back in Honors Chem. It's sometimes called the elephant toothpaste demo. I'll add some soap to it, and you have all these bubbles and foam being created. Maybe even showed you a video of that before as well. I use a catalyst. I like to use potassium iodide, Ki, but another catalyst you can use is sodium bromide solution. So you can see your hydrogen peroxide is aqueous, and your catalyst here, because it's written above the yield sign, right there, that's your catalyst, that's aqueous as well. So they have the same state, same phase, so it's a homogeneous catalyst. Something to look at here is, and we'll talk more about this in our electrochem unit, if something's occurring in acidic or basic solution, but the H2O2, the hydrogen peroxide in this case, is in a slightly acidic solution. And that's going to play a part in the next thing we look at. So we're going to look at this chemical reaction in terms of a reaction mechanism, which is what we have here. So take a second, and this is a review. What is the intermediate in the above reaction mechanism, and how can you tell? So take a second and figure out what the intermediate is here, and then we'll see if you're right, and we can move on from there. Okay, so an intermediate is simply something that is made and then used up. So if you look at the chemical reaction, what's being made and then used up, well, I see Br2 is being made here, and it's being used up over here, so they're canceling out. It wouldn't be in your overall chemical equation, so in this case, the Br2 is your intermediate. Okay, next question is, what is the catalyst? So we did talk about this before in a previous lesson, and how can you tell it's the catalyst? So make sure you answer that and explain why. And one thing I want to point out here is that hydrogen, the H plus here and here, that is not your catalyst, okay? The reason why it's not your catalyst is because if you go back here, it said that, it said that your H2O2 is in acidic solution, okay? So that H plus should be there because you're in some sort of dilute acidic solution here where this reaction is occurring. Okay, so don't worry about the H plus there. It's not a catalyst, it's not an intermediate. It's just in acidic solution, so that's why I'm crossing it out here. So what's the catalyst in the above reaction mechanism? If you take a look at it, you should end up with Br minus 1. All right, so that is being used up here in this case. So I'm using it up here, and I'm making it over here. Because remember, catalysts can be used over and over and over again. So it's something that is made, something that is used up and then made. So make sure you know the difference between catalyst and intermediate. You should be good to go. All right, so intermediate is made and then used up. A catalyst is used up and then recreated and made again. So you can use it over and over again. If you cancel things out here, cancel out your catalyst, cancel out your intermediate right there, you end up with the balanced chemical equation. 2H2O2 yields 2H2O plus O2. Perfect. So let's take a look at a reaction pathway here with a catalyst involved. So we saw something like this in a previous lesson where we looked at energy of reactants, products, intermediates, and we took a look at what maybe the activation energy was or the change in E, the delta E. There's going to be a review question on this at the end of the lesson today where we will review some of that. But in general, a catalyst operates by reducing the activation energy of a reaction. So on the screen here, same one that you guys have, you have your uncatalyzed reaction pathway in red. And you can see the chemical equation, 2H2O2 yields 2H2O plus O2. And then you have your catalyzed reaction pathway that's in blue. So make sure you have that labeled on your note sheet as well if it isn't already. And that's where you end up with the reaction mechanism that we had on the previous slide. So look at how the catalyzed reaction has a lower activation energy. If you follow that, it's generally right here where my pen is. All right, so we can see we have a lower activation energy and therefore a faster rate of reaction. There's some weird stuff going on here. Let's talk about that on the next slide. When you have a catalyst involved, you have this weird section here in the middle where that lower activation energy is located. So let's identify these things. You could label them on your note sheet. We have transition states and we have intermediates. So we need to make sure we know the difference between these two things. Usually won't be very many questions about this, but you'll have to at least be able to identify. If you're given this, how many transition states and how many intermediates do you have? So in this case, we have 2 transition states and 1 intermediate in this catalyzed reaction pathway between reactant and product. Let's take a look at some differences between these. This is not for the chemical reaction we were looking at, but I want to show you what I mean by intermediate versus transition state. So a transition state, and you could maybe make a note on the side of your note sheet here for this. A transition state is a partially bonded substance. So you can see, I just have some random ones on the screen for you. If you have a bromine molecule, so it's Br2, right? And you want that bond to break. You want the Br bond to break. That bond is going to stretch a little bit, right? So you have your bromine here and here, it's a loose dot structure. You can see the partially broken bond. That bond is stretching now. This is a partially bonded substance. That is your transition state right there, okay? It's transitioning between your initial substance and this might be your intermediate, right? Because these are very unstable, right? I mean, look at that. You have Br, 2 monatomic bromines. Really not going to happen, right? So they're going to quickly move on to something else and interact with something else. But you have your transition state where the bond is partially broken, okay? And you have your intermediate where you actually do have the 2 monatomic bromine atoms. Take a look at another one. You have this substance with a single bond and a bromine here at the end. And then what's going to happen is this bromine is going to break off of there. So that bond is going to break and it's going to interact with something else. So in this case, here's our transition state. You can see that the bond is stretching right here. And then here's our intermediate actually being formed. This is some organic chemistry stuff actually, where you're going to write some of this notation here at a later point in your life probably. So the bromine actually does break. That bond actually does break right there. And you end up with a positive charge on this structure, and you end up with your bromide ion over here. So here's your transition state, here's your intermediate, and over here underneath it's much more complex. Definitely some organic chemistry mechanism happening here. You can see that we have some partially broken bonds here, here, and here. We have 3 of them. So here's a separate transition state, and we end up with, in this case, we don't have our intermediate here, we just have our product being created. You can see what is formed there. So anyway, transition state is your partially bonded substance and your intermediate is your unstable bonded molecule. So the intermediate here, like that's pretty unstable because you have that positive charge there. That's unstable, but it is actually bonded. Okay, there's no partial bonds there. So again, transition state is partially bonded and intermediate is a unstable bonded substance. That's about all you need to know here. You're not going to have to draw these. We're not in organic chemistry, so you're not going to be drawing these reaction mechanisms. But do know that this would have 2 transition states, transition state 1, transition state 2, and 1 intermediate in this chemical reaction. Okay? So the intermediate is your valley, and the transition state, those are your peaks between reactant and product. Okay. Moving on. Catalysts operate by increasing the number of effective collisions. So how do catalysts lower the activation energy? If you increase the number of effective collisions, then of course the reaction is going to proceed at a faster rate. So a couple of things could happen here. First one, a catalyst could provide a new reaction mechanism altogether for the reaction that has an activation energy lower than that of the uncatalyzed reaction. It's kind of what we looked at earlier. Right? We had our uncatalyzed reaction pathway, and we had our catalyzed reaction pathway with those intermediates and transition states. That's a new reaction mechanism, and that activation energy is lower. A catalyst could also assist in the orientation of reactants, and you know that's important from our lesson on collision theory. the proper orientation plays a big role in how fast a reaction goes and if you have effective collisions or not. A proper orientation is going to affect the frequency factor A from the Arrhenius equation, which is what we looked at a couple minutes ago, and that's going to help increase the rate of your reaction there. All right, so we can lower the activation energy, and we can increase our frequency factor by manipulating the orientation of our reactants to increase effective collisions. All right, next one. Heterogeneous catalyst is when the catalyst is in a different phase than the reactants. So a good example of that is a catalytic converter, and we talked about these back in Chem 1 and maybe earlier in this class. But a catalytic converter is a solid, usually has like some platinum, some rhodium on it maybe, and you're going to have your exhaust from the car passing over that, which is going to be in the form of carbon monoxide and some other gases as well. So you have gases, obviously in the gas state, you have your solid platinum rhodium catalyst in your solid state, and that's going to be your heterogeneous catalyst. So there are two steps involved in this with the heterogeneous catalyst. Pretty cool to look at on the next slide. Step one is adsorption, and it's not a typo, it is adsorption with a D. Adsorption is where you bind the reactant to the catalyst surface. Once that happens, particles that bind, that adsorption process, once they're on that surface of your catalyst, the particles could migrate, and that's step two, migration to create the product that you want to create, and then something called desorption. All right, so those are your two steps, adsorption, migration, and desorption. Let's take a look at it. So here's an example where you have a solid catalyst right here, some metal surface. That's what it is. You have an H2 molecule and then some C2H4 molecule as well, some hydrocarbon. So they're going to adsorb to the metal surface. You see that process occurring here. So you see the arrows coming in. These two molecules adsorb. You're going to have some bonds being broken and new bonds being formed. You can see that the migration is occurring in this step here. We have bonds breaking. Migration is occurring, okay, with your different atoms up here. And then what you end up with is an intermediate being created, right? It says it right here. And then, the intermediates are usually short-lived, and then the bonds continue to move, and you end up with your product. And that's what we end up with right here. When the product is leaving the surface of the catalyst, that's called desorption, and that's what's happening on that last step. So you have adsorption, migration, intermediate being created, and desorption here. And take a look at your catalyst. It's still in good shape, right? It's unchanged from beginning to end, and that's what it should be. So this could be used over and over and over again for a long period of time. Some other examples of catalysts. Here's a biology example with enzymes and substrates and active sites. So if you took AP Bio, you probably learned a little bit about this, maybe even in Bio 1. Another example you guys may have experience with from biology is nitrogen fixation. And this is where you take atmospheric nitrogen, which is just N2, and N2 is very inert, very stable. It's not a noble gas, which we call the inert gases, but nitrogen is often used in chemical reactions where you want to maybe preserve something or not have something react right away. You could have it in a container of nitrogen gas because it's super inert, super unreactive. So it's not used for a lot of stuff. What we want is nitrogen in the form of nitrates, nitrites, and ammonia, and that helps with, that's one of the most important biochemical processes on Earth, which is where you take the N2, you break that bond through an enzyme, or not an enzyme, through a catalyst, all right? So nitrogen fixation occurs here, and then that nitrogen is able to be used in nitrates, nitrites, ammonia, and it's a very important process for plant life on Earth, all right? So moving on to the last slide of the day here, catalysis with a reaction pathway. I actually don't have, it's just a review from before, I don't really have a catalyst pathway on here. Let's just add one for fun. Okay, so there it is. Take a look at this. I give you some energies on the y-axis. So we have an energy here, 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 and here. Here's your reaction pathway in the forward direction going to the right and the reverse direction going to the left. And I'm going to ask you a couple questions about activation energy, overall change, endo-exothermic reactions. There's a question like this on your test, pretty easy stuff. And then there's a question like this in your homework as well that you'll work on that is going to take you a very short amount of time as well. All right, so I'll ask you those questions, and then we'll go from there and see how we do. All right, thanks guys.